Okay, so thank you, Raul, for the introduction. Had I known that you're going to read out the bio, I would have been much, much shorter. So hello, everybody. Yeah, hello, everybody. So I am Bernard. I'll be your speaker for today. I come to you from KAUST. My lab is called the Image and Video Understanding Lab. So you're going to see that logo on the bottom left a lot, the IVUL logo. It stands for the Image and Video Understanding Lab. Can everybody hear me?
Yes.
Yes.
Hello?
Yes.
Loud and clear.
Yeah, because it seemed to broke up a little bit.
As far as I'm concerned, I'm
Yeah,
fine.
smooth.
I have very clear, crisp sound.
Same here.
But can you hear us? You seem to be frozen.
Okay, can everybody hear me again? I think I got kicked off of Zoom.
Yes, you're very audible.
Okay,
Yeah,
all right.
fine. You're good.
Sorry about that. It was bound to happen. Okay, so let's start directly into the topic that we're going to talk about today. So today, instead of having a whole hour of just giving you some shameless bragging about the work in my lab, what I'm going to do instead is kind of give you as much of an overview of the landscape of a particular interesting topic that's getting a lot of attention now in the deep learning realm, or in general the machine learning realm, and specifically adversarial attacks and defenses. At the very end, I'll mention a work or two that are happening in my lab that kind of contribute to this landscape. But for the most part, the idea is to give you an overview of what this topic is and why it's interesting, why it's important, and why maybe you might be interested in it. Okay, so before that, I mean, as a kind of a follow-up to the introduction that the slides are not going forward.
You're back, Bernard.
I don't know what's going on. All right, let's try this again. Okay. All right, so before I get to the topic of the day, which is about robustness and certification and defenses for deep networks, what I want to mention a little bit is that the kind of research that my lab actually does at KAUST. So we focus in on mainly three research themes. One has, and deep learning plays a role in all of them actually. The first one has to do with video understanding. So understanding at large scale about video, what people are doing in the video, where they're going, what they're going to do in the future, and so forth. So by far, the video is considered the biggest big data out there. And so what we try to do is build tools to develop develop tools to extract semantics from video. The second research team has to do with visual computing for automation. So things like trying to teach cars how to drive, how to perceive the world around them. Same thing with UAVs and drones. We do a lot of work on learning certain things from simulation and then transferring it over to the real world. The third theme, which is the topic of this talk, has to do with fundamentals, basically optimization and other techniques for problems that show up in computer vision and machine learning. We also build general tools, for example, graph convolutional networks. These are networks that are applicable to general graphs, not necessarily images or videos, but general graphs. And this is where this is the work that we are doing right now has to do with the last theme, which is the fundamentals theme. So in terms of the outline, like I said, I'm going to give a kind of a background on what adversarial attacks mean. Then we get to defending against these adversarial attacks in two different types. One is empirical defenses, and the other one is provable defenses, where we're going to spend most of our time. Although there's been a lot of work on empirical defenses, and there's still a lot of work on empirical defenses, we'll see why those defenses actually have issues with them, and they don't have any guarantees that we'd like to have. And this is why we're going to focus more of our time on provable defenses against these adversarial attacks. All right. So for those of you who don't know what a deep network is necessarily, but they know what machine learning is usually. So you have an input X. Let's say it's an image of this cat, for example, and you push it through a feed-forward network f theta of X, parameterized by theta, and it outputs, for example, some it could have a different architecture. This is one architecture of choice, but it could have more or less any architecture that you choose, and it outputs the prediction scores for various classes. This network is tasked to classify what the image input is. So for example, you could have n classes from including dog, cat, horse, house, cow, whatever, and you get a score for each of these. Okay, so the output is a finite number of class scores going from 0 to 1, and they sum to 1 usually. Okay, so it's like, I think of a PMF. And so to infer the label, the predicted label of this image, you take the argmax, which class has the highest score is the one that you give its class label. That's the predicted label. And that's what a feed-forward neural network is. There's been a lot of advancement in what these architectures look like, how to train them, and so forth. There's been a boom, obviously, in the deep learning era, and this is why this boom is it's attributed to the fact that there's a large-scale amount of data that's available that's annotated. There's GPU hardware accelerators that can allow you to train these neural networks in time, and because of that, there's been adoption by these methods from industry, academia, and a whole bunch. And this is why we talk about neural networks more often these days, especially deep networks. Okay, so they do very well. They could produce very good performance on benchmark data sets, even though they could be large scale and diverse. So the way that we train these neural networks, i.e. estimating theta, the theta is, think of it as a parameter vector for the neural network. Theta could be of the order of millions and now billions of parameters that represent the function f theta. They could be, for example, your convolutional filters. They could be your weight matrices and your MLPs, multi-layer perceptrons. They could be whatever. They could be all the parameters that you have in the network. You define a loss that L over here that computes a discrepancy between your prediction f theta and the ground truth label yi. Okay, so for example, if you know that this image is a cat, yi should be cat, and f theta of xi, you want to force it, you want to learn theta so that this f theta of xi is cat, basically, and you want to do that for all n samples that you have in your training set. All right, so this is the typical way of training. You minimize the summation loss that minimizes the discrepancy between the predicted label and the ground truth label. Obviously, to produce PMF kind of values that go from 0 to 1 and sum to 1, we use the softmax operator S, which is the usual way to generate such probability scores at output. So the reason why we're here in this lecture is that, unfortunately, even though these networks that can be trained on millions of images and they produce accuracies that very high accuracies on large scale data sets even in some cases, reaching or even exceeding human performance on the same data set, same benchmarks. Although, despite these very highly accurate networks, they have this property. So for example, you add to it a little bit of noise, and this noise over here, that's multiplied by 0.05. I mean, this is if you add it to the original image, this cat image, you get the image on the right, and it's very, very, very similar to the one on the left. So it's imperceivable, the difference between, for the human eye. However, if you do a forward pass of the left image, you get cat, high confidence, the correct class. If you do it on the right, you get something totally different, totally wrong, actually. And you see, there's no perceivable difference, well, humanly perceivable difference between the images. Now, the question is, why is this happening? And how do we circumvent from that? This is a very serious issue, right? Because imagine, you're driving your self-driving car, and all of a sudden you get, there's some noise from your sensor, and all of a sudden you stop detecting your pedestrians correctly. Imagine you're using this system to, fly a plane or do whatever, right? Especially for life critical applications, this type of tremendous errors, this is and sensitivity to a little bit of input noise is a big issue. And these attacks, these are the ones that you can design so that you add them to the input that create a wrong prediction. These are called adversarial attacks. Okay, so why do they come up, and we want to circumvent against them? They come up because of how the decision boundary of these neural networks are found. You can see that the in decision boundary of these neural networks, they're very, very jagged, and this is why these adversarial attacks actually show up. However, I mean, just these additive attacks, these additive perturbations that don't change much the image, you might think, okay, maybe they're not really natural. Right? These small attacks might not be that natural, and therefore they don't occur in the real world. And why should we care, right? So if they don't occur in the real world, you won't be able to break a world system. However, there are natural adversaries, right? So people actually hacking into systems to break them. So, for example, this is an example from the Tencent Security Lab in 2019, where they had a Tesla car running on autopilot. And they added a few small stickers on the ground. On the left, you see them here on the left where the arrows are. There's these very small stickers on the white stickers on the ground that basically made the Tesla car think that this was a separate lane and therefore do some erratic behavior. So basically, if you were a malicious person and you knew that there was such a issue with the Tesla autopilot, you would go around and put these small white stickers all over the place on roads to make it, get confused and break the system. So naturally occurring adversaries do occur, right? And they do exist. And so, of course, we want to circumvent against those also. So it's a serious issue. Here's another example of a physical attack, or natural attack. So on the left, you see the results of an automated object detector. This is a method that a neural network-based method that takes an image and draws a bounding box around every single object, and it gives it a label, right? With a probability score. So for example, laptop has a 78% score, bottle is 54%, cell phone is 51%, and so forth. So it does a very good job in detection. However, if you hang up a picture of some zebras, for some reason, you no longer detect the rest of the objects on the table, on the right. And this has also been shown. These are physical attacks that of adding things to the scene that leads to these weird behaviors. So how do we circumvent against that in training and understand it further? We have to come up with a formal mathematical formalism, really, for what these adversaries look like and how we can how we can deal with them. So usually what we do is we define something called a threat model, meaning a model that defines how adversaries are created. And a typical threat model is this worst case additive threat model. And what I mean by worst case additive threat model is that it tries to find a perturbation delta, which when added to X maximizes the loss. Okay, so usually when we're in training, we're trying to minimize the loss, meaning that we're trying to get our predictions as close as possible to the ground truth. However, here in this case, because delta is an adversary, is trying to make the prediction as far as possible away from the ground truth. So delta here is trying to maximize the loss of the discrepancy between the prediction and the ground truth. It is an additive threat model because it adds to the input X. Now, of course, later in the very last slide, actually, when we talk about future work, is this threat model that realistic? Can we update it? Does it have to be additive? Could it be, could it have more structure and so forth? So yes, I mean, the idea is yes, but the vast majority of research that has been done here has been done on this type of threat model, maximizing a loss of the loss of the prediction versus the ground truth, subject to an additive model. But this additive perturbation delta cannot be infinite energy, right? If you allow it to be infinite energy, then it could just destroy the image, the original signal X, right? The original image X. So this is why we define some kind of a low, bounds on what delta can be, and we usually use a P norm. It could be an L2 norm, L infinity norm, L1 norm on what delta could be. It's like the energy of the perturbation that you add, and it has to be bounded by R. So the idea is that can you find delta that when added to X, you maximize the loss. Now, you're not guaranteed that you will be able to flip the prediction, right? Because you're trying to maximize the loss. That maximum loss doesn't mean that you're going to actually fool the network, but in many cases, you will be doing it. And this is the worst case scenario, right? Because if you maximize it truly, then you can't get a worse loss. That's the worst loss that you can get. And if it doesn't flip the network prediction, nothing will, right? But if it does, it does, right? So this is kind of the worst case. Yes, Raul.
Just a simple question. Theta is still chosen in an optimal way. That is, do we have a maximum of delta and inside a minimum with respect to theta?
Yes, I'm getting to that. I'll throw an equation on that. So right now, so think of it this way. So if I wanted to create an adversary on a network that's already available, that means I gave you a network f theta of X that is given to you, and I told you attack it. This is one way to create an attack. Okay. Now, what you're thinking about is how do I use those in training, right? So adversarial training, and we'll get to that in a bit, maybe even in 2 slides from now. So that's a good point. But this is how to create an adversary, right? It's something that maximizes this or tries to maximize this, is the one that's trying to actually fool the network the most. This is the worst case scenario. Of course, there's average case also. So instead of the worst case, you can have in expectation tries to fool it. We've done some work there too, but I'm not going to talk about that. The worst case is usually the most prevalent in the literature right now. So this, the minimization that we saw before for training, here, remember, here we're trying to minimize over theta of the discrepancy between the loss of f theta of xi to yi. This is the nominal training. This is usually what you do for training, right? So you have some clean images xi, you have the ground truth labels yi, you try to find theta that actually minimizes discrepancy. Great. So instead of doing that, how can I involve in there the idea of, or the notion of adversarial attack? So instead of minimizing the summation of this loss, and this is what Raul was saying, ideally what we want is minimizing over theta, the thing over the samples that maximize the loss. This is kind of, we're trying to minimize the worst case loss, okay? And of course, this is something super difficult, obviously, because theta, so forget about scalability. Just of course, theta is in the millions, and n could be in the millions or more. Number of samples. You have to do it in a batch way, a stochastic way. It's a mess overall. But that internal maximization is in itself very difficult. And there's lots of methods here and there or approximations to try to figure out how to solve this. But this is the core idea. The idea is that I want to minimize the maximum, the worst case loss. Subject to these additive perturbations delta, subject to that budget, that R budget where it can't go beyond. Okay, so the simplest things to do is how do you deal with that internal maximization, right? So we don't know how to do that. So that's, and also it's a very hard overall optimization problem, because remember, this delta is per xi. So if you had millions of xi's, you're going to have to create a maximum worst case scenario, right, for every xi, right? So it's very, very difficult to do this optimization, very computationally expensive. All right, so then what do? What typical methods of trying to resolve this is that, okay, instead of doing the maximization internally, what I'll do is at every epoch that I have, whenever I have a current estimate of theta, what I'll do is I'll freeze it and I'll create some adversaries for every xi that I have under that network, right? Under that theta, let's say theta k, okay? So at theta k, at iteration k, I'm going to freeze that network and I'm going to produce adversaries for that network for each of the samples, right? And what that means is that I will try to maximize that loss internally inside the optimization for delta. Now, do you do it with one iteration or do you do it with many? Again, you could do proximal gradient descent, which is the thing on the bottom. You could do FGSM, which is this fast gradient sign descent, where you only do one iteration of it. Anyway, there's various things to do. Keep in mind that you're going to have to do this for every sample in your training set, and this is for every epoch of training of theta. So if you do too much of this optimization to find the worst case scenario, worst case perturbation, you're going to be expending a lot of computation just to find that. So people just do a few iterations of PGD given the current network for each of the samples, and that's it. There's been a plethora of papers out there on how to make it better. So basically, how do you make it cheaper to do? So for example, do you need to do this PGD from scratch in every single epoch of training of the network? The answer is no. You can do it in a faster way. How do you improve it? And there's a whole bunch of papers on this actually. And how does this affect overfitting onto the data set? I mean, a lot of these things have been recently looked into, but here's the idea. So the idea in the majority of these defenses that create adversaries during the training, right? So basically, what you're doing is you're creating them during training so that you can learn to be to beat them. Okay, so you basically create them in every epoch of the training, and then you update your network parameters so that you beat them at the end of the iteration. So this is basically you're creating adversaries and updating the network and together jointly. So many of these adversaries that you create during training, they're first order methods. So basically they make use of the gradient of the loss, right? And so the assumption and the kind of the myth, well, I don't want to say myth, but I mean the usual assumption is that these first order adversaries do better than the zeroth order adversaries, otherwise known as black box adversaries. So the ones that don't have access to the gradient. And so, the idea is that, okay, if I want to create a defense against these attacks, what do? Well, what I'll do is that I'll construct networks, deep networks, that obfuscate or corrupt the gradient so that these first order methods don't do well in breaking the network. And so there's been a plethora also of papers, or not plethora, maybe several papers on this idea of how to kind of defend against such first order attacks, and by kind of hiding stuff about the gradient or obfuscating it. So for example, this is one paper that did something along these lines, where it would randomly transform and resize and pad the input image, and it would give it to the network, right? So by doing this randomization, it's able to not get affected by this type of PGD attack. However, we'll see later that there will always be an attack that can actually break this defense. Other defenses, try to come up with various types of layers that actually, again, obfuscate the gradient. They have updates to the ReLU activation, which is popularly used to do something called the K winner take all kind of activation map, where only the top K activations, top K valued activations get passed through. Otherwise, you put them as 0. And since you don't know what that threshold is at every single layer, it's very hard to propagate the gradient for in the adversary. But irrespective of that, right? There's been papers that have contributed to these types of empirical defenses. But there's been other papers that show that for every defense out there, you can have an attack, either a first order attack or even a black box attack that actually can break it. And in the end of the day, as a take-home message for you, when we talk about adversarial accuracy of a network, that means if you give me a network and I tell you that I'm trying to describe its adversarial accuracy, It's basically the worst possible accuracy that one can attain under all the threats that satisfy the constraints of the threat model. Okay, it is the worst possible. Okay, and this is why, I mean, there was this, there's this plethora of empirical defenses and then subsequently attacks that break them and so forth. So it's like a cat and mouse game. These defenses that we showed before about obfuscating or hiding the gradient, they can be easily attacked by these types of attacks, these EOT attacks, which are, if you're going to randomize the input to produce to try to obfuscate the gradient, what you could do is randomly transform the input and then do a forward pass and then average out the gradient of this to kind of guesstimate the real gradient. Also, what you could do also, if you, for example, you have a black box network that you don't know what its architecture looks like, what you could do is approximate it with enough probing, with enough input-output samples. You can actually estimate a differentiable network that can approximate this black box, and then you just do regular attacks, first-order attacks on it. So basically, what I wanted to say is that these methods that have come up have given us a false sense of security. Okay, and there's been papers on this actually. So what I mean about this is that for all those defenses that you see that I mentioned, right, and a lot more, whenever they come out, they're quickly afterwards there's a defense, there's an attack on it that actually breaks it and makes its adversarial accuracy 0, basically. And this is a table from a paper that showed that. Those of you who work on MNIST know that if your network doesn't reach 99, 98%, it's not that great. So getting an accuracy of 55% on MNIST is very bad, basically. So basically, this idea is that with these empirical defenses that we're coming up with, that trying to approximate this threat adversary during training, and trying to target particular attacks and to defend against them, there's always other attacks that will come up and that will break the defense. Actually, and I think in either ICLEAR 2018 or 19, there was like in 9 or 8 papers published or under review in ICLEAR, because it's an open review kind of forum. These defenses were, of course, they showed that they were very good against particular attacks in the papers. But by the end of the open review period, I think 7 out of the 9 were broken already by people in the community. So what that means is that, I mean, for every empirical defense you have out there, there's an adversary that can break it, unfortunately. But I mean, the good thing here is that there's a benchmark. You can go and upload your results. It compares your defense or evaluates your defense against various applications or the various versions of attacks out there, especially this auto attack that is basically an ensemble of many attacks out there in the literature. It's called Robust Bench. It's a robust benchmark. It's very well done. It stays up to date, and you can see basically what are the most kind of reliable defenses out there, in empirical defenses out there. Right, but there's no guarantee that whatever defense out there that you come up with, although it does well on the benchmark, there's no guarantee that there might not exist a new attack that might break it. This is the major issue here, right? So basically, even if you do well on the benchmark, this adversarial benchmark, that means among the adversarial attacks that we know of, if you're doing well, it doesn't mean that there won't be in the future an attack that could break it. So this is why I'm calling it empirical, or people call it empirical robustness or empirical defenses. But we don't, I mean, those are, we might not want that kind of robustness, right? We might not want that kind of defense. We want something that has provable guarantees. And so on the other side of the coin, there's these provable defenses, right? So instead of kind of approximating that maximum, remember when we were treating the optimization and there's a maximum, there's a min-max kind of problem, instead of kind of approximating it and doing kind of a whole bunch of cutting corners, trying to find the adversaries in training, is there any way to actually find that exact loss in the input space? However, so the methods that do that are called verification methods. And they target trying to actually compute and reason about the exact maximum loss. So there's no cutting corners. Unfortunately, they only really apply to very, very shallow networks. We're talking about 2 or 3 layers only, so they're not realistic. And even though you can verify a network to see whether it's verifiably robust within a region, you cannot actually integrate it into training because it's so slow. So even trying to certify a network that's already been trained, integrating it into training is very, very slow. So these methods usually are not practical. Now, on the other hand, there's these so-called certification methods. They produce certificates that guarantee that there does not exist an adversary within a region, right? And they do this by, instead of treating or reasoning about the exact maximum loss, they look at kind of bounds on it. So for example, an upper bound to the maximum, and they look at that instead. And they still can generate provable guarantees that an adversary does not exist within a region around the input. They scale much better than verification methods. They can apply to ImageNet and these big data sets, as well as big architectures. They do sometimes produce false negatives, okay, and they do not scale. Most of them, some of them do, but most of them right now don't scale well during training. But at least it's possible to train with them. So in the rest of what I'm going to talk about, we're going to talk about network certification methods. But before that, let me just give you one flavor of what a verification method is. And this is a typical variant of it. It's called IBP, which is interval bound propagation. So again, verification is the idea of verification is that you want to try to kind of exactly compute what the maximum loss is. Okay. So what IBP does, it's a well-known method before, but this paper here was kind of the first to show that, or come up with engineering kind of heuristics, let's call them, to get it to train on big data sets. Okay, but the idea is very simple. So imagine you have some kind of network, and this network is a composition of particular operators, and your input is ranged from a certain from A to B, let's say, like an interval of A to B. It could be in multiple dimensions, by the way. So, but let's say you had a scalar input, and it varies between A and B. All right. So the question is, like, after you go through the first operation, which is this 2D convolution, what is the lower and upper bound of the activations of the output of this convolution? Okay, so you're propagating the bound. So if the bound started from A to B in the first the input, what is it after the first layer? What is it after the second layer, and so forth? And so, with convolutions and ReLUs and linear units in general, you can do this kind of bound propagation. Of course, the bound gets bigger and bigger and bigger, and it might not be meaningful at the very end. But if you could train in such a way that that this image is a cat, right? So the cat score, its range of scores with respect to the input, the ranges. So because if the input ranges from A to B, the output will also range from something to something based on this propagation, right? Can you train the network in such a way that the cat score, its range, its lower bound of its range, the lowest score possible, is higher than the maximum, the upper bound range of all of the other classes? If you can train the network to do that, then you are guaranteed that you cannot basically add any kind of perturbation to this cat image and flip the prediction from cat, because you guarantee that the minimum and maximum, or at least the minimum score of the cat, is higher than the maximum score of any other class. Okay, so this is one verification method, but like I said, it's computationally expensive in many cases, and it doesn't scale well with the data or with the network. So let's focus in on certification methods. So this is where we're going to talk about certified robustness. They give guarantees of robustness, but they could be more expensive than empirical defenses in training and test. But let's see how they work. This is a snapshot from a slide from Zico Coulter, who kind of popularized this idea of randomized smoothing. We're going to particularly talk about randomized smoothing as a way to do network certification. Again, what does that mean? Basically you give a certificate that this network produces around an input X a constant prediction, meaning that there does not exist, because if it creates, if it knows that within a region of size let's say R, around a current input X, if the prediction is constant, right, it means that there is no adversary. Because if there was an adversary in this region, then it cannot flip the prediction because the prediction is constant. So that's kind of the idea. And so if you look on the left, the plot on the left, this is the usual kind of decision boundary that you see. You have blue and orange, right? So you have two classes. And if you're at that point in dark, right, and there's that kink in the decision boundary, you see that, you know, there are adversaries, you know, i.e. orange points close to that point in the blue region, whereby if you move from the blue region into the orange region by a little bit, you can actually flip the prediction, right? And so the idea is, the whole idea of this randomized smoothing is that how can I, instead of using f of x, which has these kinks, these sharp kinks in them, can I smooth out the decision boundary? That's the idea. If I smooth it out, then you see the plot on the right, you see that that kink is smoothed out and you have more of a range to, you're basically getting farther away from the decision boundary, and therefore you're being more robust to input perturbations. So instead of looking at f of x, right, this is what randomized smoothing does, you're trying to replace it with a surrogate smoothed out function g, which is of this form. This is one of the various forms of this smoothed out classifier. Basically what it says is it's just a fancy way of saying that it is a majority voting classifier. Okay, so what does that mean? Let's do it formally. So if you want to create a network F that is robust to perturbations, certifiably robust, okay, its prediction within the region delta has to be the same, meaning f of x and f of x plus delta is equal no matter what delta is in capital delta, the set. What that means is that there does not exist an adversary in this region. This is why it's certification, right? It's, you know, you guarantee that there's no adversary attack. So no matter how much you try with PGD or any of these other attacks or these other variants, if you have a provably certifiable network with a certain radius, you know that as long as you stay within that radius around the input, there's no way that you can create an attack. And this is kind of what we need, right? We need to prove that the network will not be fooled within a region of its input. And so this G function, which is the smoothed out version of your network F, is basically defined as this. It looks complicated, but it's very, very simple. So imagine you're at a point X in input space. You add to it some Gaussian noise with a certain sigma square I covariance, okay? You add to it, and then you probe the network at that point. And you see, you know, if you do it enough, you see like what is the likelihood of getting class C as your prediction, and the one that has the highest vote, okay, is the one that you take as G of X. So this is why it's called a majority vote smoothed out classifier. So basically, you look at a region around you and you say to yourself, okay, I predict mostly blue, so I'm going to let G of X at that point X predict blue. And by doing that, you can have there's a really nice theorem from the original randomized smoothing work, which is actually it's well known from previous work, but this was the first time it was used for the kind of idea of network robustness. You know, if you look at the theorem, it's pretty simple. It basically says that if your network produces in a region around X, if the majority vote is the class CA, okay, that's kind of the class that you usually predict with probability PA. And the second majority one, that means the second class that is, you know, has the highest frequency to CA, that happens with probability PB. Okay, so if there's enough separation between the majority vote class and the next runner up, okay, i.e. PA is you know, we're trying to make PA and PB as far apart from each other as possible. If you make them farther and farther apart, this function G, not F, but G, is actually stable or robust within a region of this radius in blue on the bottom. Okay, what does that mean? That means even if you add a perturbation delta to G, okay, it will always produce the output CA, no matter what that perturbation is, so long as it stays within the radius R. And that radius R is called the certification radius. And we want that radius to be as big as possible, because if you make it bigger and bigger and bigger, it means that there doesn't exist an adversary within the range. within that region that fools the network. So it produces a constant prediction, CA. All right. So this is an interesting theory. It basically says the more and more this majority vote is highly probable, meaning that it's a strong majority vote class, i.e., it's much bigger than PB. Then that difference between the sigma inverse, sorry, psi inverse PA minus psi inverse PB, that thing gets bigger and is multiplied by sigma. So with the larger smoothing variance sigma, you get a bigger radius. Okay. But you have to keep in mind that PA and PB are a function of sigma also. They're not independent of it because they rely on what epsilon is, the perturbation that you add is. So keep that in mind. So this is a great theoretical work. I mean, basically it shows you that if we can kind of treat or manage this smoothed out classifier G, we have a provable radius within which there doesn't exist an adversary. This is something very nice. And we have kind of a nice compact form for what R should be, the radius of the certification region should be. However, there are questions come up, obviously. So first and foremost, okay, this is great. This smoothed out classifier G is certifiable in this radius. That's great. But does it mean that the more smoothing we do, that means that as sigma gets bigger and bigger, does it mean that the certificate is better and better? The answer is not necessarily, because like I said, PA and PB are a function of sigma. If you increase sigma, it means you're smoothing more harshly. Your PA and PB might get closer to each other. And therefore that difference that you see in the radius gets smaller. So it's not necessarily true that this radius just increases linearly with sigma. This radius that you have here has nothing to do with accuracy. Because remember that CA that we saw before, the class that is the majority vote, nobody told you that this is the correct class. It could be a wrong class. It is the majority vote class for sure, but it's the wrong class. So this radius that you have here doesn't certify that you're actually, it certifies that there's no adversary in the region that flips your prediction, but your prediction could be originally wrong. And therefore, this idea of smoothness, randomized smoothness, this radius R, should be integrated into training somehow to be able to incorporate accuracy, right? Meaning getting the prediction correct and getting it constant as much as possible within a region. And then the question is, how do I, of course, I want this radius to be as big as possible. How do I increase it? So those are things that we're gonna, that several papers have been come out to tackle them. The first one is this one, which basically took this idea of randomized smoothing and integrated into training. And actually it showed that, I mean, with very simple changes to how you do nominal training, you can actually make something certifiably robust with very simple updates. So here's kind of the logic. Remember, we wanted to, kind of the majority vote class, right? We wanted to be correct. So instead of assuming it to be CA, we want to force it to be CI, which is the correct class for element XI. Okay, so if you do some treatment and you do some approximation with the softmax, this thing on the second row is on the right is the softmax, and you rewrite the loss and you use Anson's inequality, you can show that trying to train a network that is certifiably robust, right, is equivalent to, in some way, under some kind of assumptions, because they use Anson's inequality. But anyway, it is as simple as doing so-called Gaussian augmentation. What does that mean? That means, let's say I gave you your training images XI and the labels YI, and I want to train this this network to be certifiably robust. So what do? I take my clean images XI, and then in my training set, I augment it. I increase the training set by adding some Gaussian random noise to it of a certain distribution, certain covariance, and then I train in a nominal way. Yeah, that loss function that we saw before, the summation loss over all samples, you do the same thing, but now you have Gaussian perturbed images in addition to that. So that will lead to some certifiable smoothness. That's not the only paper out there that did it. So another paper is Macer. This one is a more recent one. Basically, the idea is that since you want to, since you want the maximum radius, why don't you take that radius and plug it into the loss function itself? So I want the training loss, the kind of the prediction discrepancy, the discrepancy between prediction and ground truth labels to be minimized, but I want the radius to be maximized. So they take this kind of radius and then plug it in as a regularizer within training. And by doing that, basically you're trying to train the network so that you can actually, get good accuracy on the clean images, but also get as big of a radius as possible. And the extension to this is that instead of looking at G as your just a majority vote classifier, smooth classifier, it's an highest expected score classifier instead. So instead of a probability, argmax probability, you have an argmax expectation instead. And that makes certain things simple to make it differentiable when you add it to the loss function in training. So basically, you take the bottom. You take the bottom, in equation 16, you take that exact expression for the radius and you plug it in as a regularizer in the loss to be able to maximize it, right? So that means you're trying to train the network, estimate theta such that it minimizes the loss on the clean images, but also maximize the radius, giving this randomized smoothing pipeline. So you can integrate exactly into the training. And there's been a plethora of kind of randomized smoothing papers ever since. So this idea of randomized smoothing it got really hot because of the fact that it can, it's very scalable. All what you need to do is either add Gaussian noise or add a regularizer. It's not that computationally more expensive than nominal training, right? Evaluation might be expensive because you have to certify certain regions, but training from a training point of view, it's not that expensive. And there's been many papers on there recently trying to improve its, improve the radius, the certification radius, and trying to make it more efficient and so forth. What have we done? So in the last 10 minutes that I have, I want to talk about a little bit about what we have done in my lab on this. It's an exciting problem in general because it has to do with guarantees on what deep networks can produce. And this aligns with the push towards reliable AI. If you've heard of kind of these adjectives in front of AI, like trustworthy AI or reliable AI, this is aligned with that, because you want a deep network that can produce for you some predictions that you're confident that they are correct, and they don't just change if you add a little bit of perturbations here and there. Right. So this is why, kind of going down the route of this certifiable robustness is something very, very important that even especially industry is very interested in. Because imagine, for example, you're trying to get a government approval for a machine learning method that is based on deep network. And the government body asks you, like, where does this thing fail? And can it easily fail? And your answer cannot be, I don't know, right? Obviously. So if you can get some certification, like you give a guarantee that as long as the input doesn't get perturbed by this much, I can guarantee that the prediction is going to be the same or correct, or it doesn't change much. This is something very important that it's something very important to work on. And so what we've done at Evil is that we've extended kind of the randomized smoothing idea further to make it more applicable to real world problems. So these G functions that you have, these are either the majority voting functions, smooth classifiers, or the expected score smooth classifiers. The idea is that you see here, you see a sigma square I. So what does that tell you? That tells you that every, this is a multivariate Gaussian that you add, right? Say epsilon is added to X. And if X is an image, then epsilon is also an image. And so it's like a Gaussian random image with IID entries. And so every pixel is basically treated the same, right? It has the same variance, it has the same everything. And this sigma is the same for every pixel. Now, of course, the question is, how do you do better? And this is kind of the kind of graphical idea of why we can definitely do better. So on the left is what people usually do in randomized smoothing. They say, you know what, I'm going to smooth this input element out x1 or x2, x3 using a sphere of this size sigma. And it is the same sigma everywhere, right? X1, X2, X3 have the same sigma. However, one has to make a distinction. And the farther you go into the decision boundary, that means the farther you go into the left, the farther away you're from the decision boundary, meaning that there's less risk that you will flip the prediction, meaning that your certification radius should be bigger. However, as you get closer to the decision boundary, your certification radius was expected to get smaller, right? Because if it's really close to the decision boundary, very quickly do you you extend beyond your correct label, and then you can you get a flipped prediction. And so the idea here is very simple. It's basically, how do we make sure that the sigma that we smooth with does vary depending on where you are with respect to the decision boundary. And this is what we call data-dependent randomized smoothing. And so, the formulation is very similar. Instead of having sigma square I, we have sigma square of xi. So the question is, how do you pick sigma square of x in an optimal way? Well, all what you need to do is try to solve for the best radius. So what is the maximum rate? What is the sigma that produces the maximum radius? Okay. And keep in mind that, remember what I told you, that PA and PB that's inside, these things, that's expectations, that you see inside, these are a function of sigma. Okay, so it's a very nasty optimization, and especially since sigma is a parameter in the distribution that you have to solve for, it makes it even more complicated. So in order to make this thing data dependent, that means for every x there's a sigma x. Okay, you need to solve this optimization. So how do you solve it? Well, I mean, what's interesting is that in the way that is right now, because it's expectation, it's very hard to come up with a compact form for the expectation. If you want to go down the route of sampling, you're sampling based on an unknown sigma. So it gets very complicated very quickly. So instead, we adopted a method that's a typical trick in variational autoencoders and in optimizing the elbow, that we do a reparameterization trick. Very simple. So instead of having this epsilon be in a distribution that has the variable inside it, you just do a change of variable. And now, if you look at the sigma x star equation on the bottom, you see that now the epsilon hat is just a standard Gaussian, and now you have sigma inside the function f. So at least now you don't have to deal with weird sampling strategies. And now that you have it written down this way, this expectation can be approximated by a summation, by an average, and you can do some gradient descent, or sorry, in this case, gradient ascent, to find what sigma x actually should be. And so algorithmically, it's very, very simple. So you basically you take your input x, you add to it some Gaussian noise, modulated by your current estimate for sigma x. All right, you do a bunch of these, you average them out to find what EA and EB are, and then you do a gradient ascent step, because this function is differentiable. That's all what you do. So basically, and this can be done very, very, very efficiently, because keep in mind the sigma x is just a scalar value. So you're doing scalar updates, which are very, very fast. So by doing that, for every single x you have, you get a separate sigma x. That means you're smoothing the input space with different sigmas depending on where you are. Now, how do you integrate that into training? You can do this in inference time, right? By optimizing sigma x at every input x given a fixed f theta. But how do you incorporate this in training time? Well, you can take any of your, any of those randomized smoothing methods that I told you about, Maser or the like, and then instead of smoothing with a fixed sigma everywhere, you just solve, find the best sigma for each of the samples at every single epoch, and you train with those instead. That's it. So it's it can be integrated within any randomized smoothing method that assumes that the sigma is the same for all points. And we showed, I don't want to bore you with some results. The results are very, very good. And the reason why is that, like I said, there are certain elements in the input space that can be certified with a much bigger radius than what was done before. And this is what this is what we're able to successfully do. So here on the top left corner, if you see the plot, the things in red are basically the usual randomized smoothing method that assumes a particular sigma, let's say 0.12 in this case, okay? The plot that you see here is on the y-axis, you have certified accuracy, and the x-axis, you have this L2 radius. What does that mean? That means, for example, in the top left plot, for a radius of 0.25, you have a certified accuracy, let's say, of 70%. What does that mean? That means 70% of your test set, okay, has a certified radius of at least 0.25. Okay, what does that mean? That means that you're guaranteed that within 0.25, around any input in your test set, there are no adversaries, okay? And there's 70% of them have that property. Now, as you make that radius bigger and bigger, obviously, because not all points have a very large radii, the percentage, the certified accuracy gets lower and lower and lower. But as you see, at certain point, it just becomes zero, because there's certain radii that can never be established. But in our case, with DS or DS squared is basically data dependent smoothing, but in training and in test, it's a little bit better than that only in test. You see that the curve is much smoother and gradually decays to zero. The reason why is that those elements that are farther away from the decision boundary, you can certify them with much bigger radii. All right. So basically, Cohen et al. Is just one method of doing randomized smoothing that we can integrate data dependent smoothing inside it. And you could do the same thing. I'm not going to bore you with more tables. You could do the same thing with another randomized smoothing method from Salman et al. And you could do another one with Macer. All of them, you show improvements using DS, data dependent smoothing. All right. So here are some qualitative examples of what it means to use different noise variances for different images. It basically tells you that certain images are easier than others to classify, so they could incur more. You can allow for more noise to be added to them. And what that means is that if you can classify them with this much noise, the certification radius is much bigger. So you see here in the there's 4 examples here. You have a clean image and a sigma 0, which is the usual kind of constant sigma that's used in randomized smoothing, and the sigma x star that we solve for. You see in the building case, you see that it's much higher than that of 0.25, much higher than the standard sigma 0. But for other images, 0.25 is too high. That means these images are closer to the decision boundary. That means because they're closer to the decision boundary, the noise that you're adding might be too much, and it might make them flip over to the wrong side of the decision boundary. So basically, even the qualitative results actually kind of make sense why you should have data dependent smoothing and have the smoothing factor be different depending on the image itself. So the take home message is really, and I'll end with a kind of some future work that you might want to look into. We are definitely looking into them. But the take home message right now is that network robustness is a very important topic now. We need to make sure that these highly accurate networks that we're training are also robust to perturbations. Empirical robustness measures or defenses there's so many of them. However, keep in mind that there's no provable guarantees, meaning that you never know in the future where there might be a new attack that comes out that can break them. This is why maybe we're more interested in certifiable robustness, certifiable defenses that can guarantee that there does not exist an adversary in a certain radius around the input. And one very well-known or popular framework for this kind of certification is something called randomized smoothing, which smooths out the classifier by either doing majority voting or kind of average voting within a region using this Gaussian smoothing. This Gaussian smooth classifier can be shown to have some nice guarantees of robustness within a radius, and this radius can be analytically determined and computed. And so now the question is, how do you integrate this nice theory into into the training pipeline? How do you make it more efficient and so forth? But of course, there are lots of future work. And the DS work, the data dependent smoothing work that I mentioned is just an example of that. So why should the smoothing be the same everywhere in input space? It doesn't make sense. You can get better certification if you smooth in certain regions more or less than other regions. Another thing that could be worked on, and this is what we're working on ourselves, is that instead of having a Gaussian, isotropic Gaussian, that means a sigma square I kind of Gaussian, why treat all the pixels the same? Why not treat them in differently? Meaning, instead of certifying a sphere around a point, why not certify an ellipsoid around the point? That kind of generalizes the idea of certification to certification volume. So instead of spheres as being your typical volume that you certify, how about we certify bigger volumes that have various shapes, ellipsoids, for example? that are different from spheres. Also, what about other threat models? So this is something very important, because you might think that these additive models have a lot of give us really nice properties when it comes down to the mathematics. However, for example, let me give you an example. If you take an image and then you translate the same image to the left to the right by a few pixels, and then you take a difference between those two, okay? This perturbation is not a additive perturbation. This thing is basically it's an additive, but it's a very big norm additive. But it's just a simple deformation, spatial deformation in the image, that if you take a difference between the image and the translated version, for example, the L2 difference between them is humongous. However, semantically, this is the same image. You just translated it by a few pixels left and right. So the idea is that this additive threat model may not be the most realistic. And so, for example, examples of this, of extensions of this is the following. Can you come up with certifiably robust networks to deformations, meaning rotations, translations, affine transformations, general, flow fields? These are the kind of certifications that could be also very, very interesting. The reason why is that these are more natural, right? So having a rotation or translation or a scaling of the image is more of a natural perturbation than just adding some noise. Because think of it this way: like, how about if the network is really good at additive noise, but for example, if you zoom in or zoom out from an object, meaning scale, make the scale bigger or smaller, you also want your network to be robust to those kind of scale changes, and those don't lie within the realm of additive threat models. So we were also working on that, and that's actually a very important line of work to make these certification results more realistic. Because right now, unfortunately, although it's really nice math and really nice work, and people are innovating, but in the end of the day, these additive models are not maybe necessarily that natural occurring. So if we can bring in natural perturbations to the realm of certification, that would be a great thing to have. Another thing is to better trade off between certifiable robustness and nominal accuracy. And what I say about this is that usually when you make things more robust, you make them less accurate, unfortunately, because you have these two terms that are competing against each other. You want something to be very good at particular clean images, but you also want them to be generalizable to regions around it. And so sometimes there's a trade-off. How can we create a better trade-off between them? So can we get us something that's certifiably robust, but its accuracy at the clean images without perturbation to be as good as nominally training it? That's kind of the question here. It's an open question still. And here's a very, very interesting thing. All the perturbations in the threat models that we've looked at are perturbations in the input space, okay? Because you're doing f theta of x plus delta. Now, because we're studying the sensitivity of the network to input perturbations. Now, the question here is that, can we look into perturbations not in x, but in theta? Okay, that means in the network parameters. So instead of having f theta of x plus delta, you have x theta plus delta of x, or at x. So now you're looking at network parameter perturbations. Now, why is that interesting? And is there a relationship between network certification against input perturbations versus network certification against parameter perturbations? Why is that interesting? Because that has to do with a lot with very important tasks in machine learning, where you're learning from multiple tasks, right? You learn from task 1, and then you want to learn from task 2, but you don't want to forget what you learned from task 1. So this idea of parameter perturbation might have a nice relationship to remembering knowledge from previous tasks, right? Because if you make sure that your network parameters lie within a certain radius of certification, where their predictions on a previous task are the same, and as long as in the next task you don't go outside this region, you basically have remembered everything that you learned from the previous task. And so this kind of idea of domain transfer learning, or continual learning with different tasks actually becomes possible. So is there a way to go beyond just additive perturbation certification to or input certification to network parameter certification? That's also, I see a lot of value in that too. And with that, I conclude. I'm a little bit over time.